Um, Honestly, I wish I had time to go to the bathroom before I came to this class, but I tried, but all of the facilities were being used, so here I am. We might get out early. Let's see.
Have the tea stand over here and take a phone call.
I'm happily I'll turn you loose, so no problem, and then I'll just go, and I'll come back. And I'll try to remember to turn the audio off on this. All right, get the iClicker quiz up. How are you guys doing? Tired? Me too. I made it through lunch on Monday and I was ready for it to be Friday. Ready for a nap?
So I left my iClicker at home and I got the app, but I can't figure out how to add the course. Like if I do math 113, it says we didn't find it.
Good talk. Emily, where are you? Good talk to Emily. Okay, thanks. Who would like to start us off with a prayer?
So this thing that
Thank you.
I'm thinking about was
Okay. Dear Heavenly Father, we're very grateful for this day, for the chance we have to be at this wonderful university. We ask that throughout our class today that we may receive the thoughts we need to learn this material. We're grateful for all the many wonderful things that thou givest to us.
Thank you. Okay, while you're working on the iClicker quiz, I'm just going to share an experience that I had last night. How many of you have seen The Fighting Preacher? Yeah. What, only one? You guys haven't seen the movie The Fighting Preacher? Yeah. Yeah, we'll show it in class. Wow. You guys should definitely go see it. So the premise of the movie is about this family, this couple who gets called to serve in Palmyra. He happens to have been a boxer, but they end up serving their mission in Palmyra for like 24 years and trying to combat the hostility that's been there for so long. Well, a lady in this won't mean as much to you if you haven't seen the movie. But, a lady in my ward, before she was a year old, her family was one of 3 families that moved out to take the place of the Bean family that the movie is about, The Fighting Preacher. And she gave a fireside last night, and it was amazing. So her first 8.5 years of life were spent growing up in Palmyra. So they sent 3 families out because part of the Bean family, their responsibility was to try to buy the church history sites as much as they could, especially the Hill Cumorah. They had bought the Joseph Smith home already, and that's where they lived. And by the time that the Beans left, they had the Hill Cumorah and they had a couple other farms. And so 3 families went out to take care of 3 farms and to proselyte and do whatever. And so she lived on the backside of it. She helped to run the farm on the backside of the farm. So it was kind of cool. But they faced a lot of the same things that the Beans faced when they first went out there. When they went to take the kids to school in Manchester, technically they were in Manchester Township, the parents didn't want any Mormons in the school. So the moms had to go with the kids for the first 2 weeks to show that they were going to be good kids. And it didn't take them too long before they were the model citizens. Right? When they were graduating, her older sisters were graduating, she graduated top of the class, and they just loved her. But at the beginning, it wasn't easy. And in the movie, you'll see a girl, one of the Bean girls, stuck in the back of the class with the chair facing the window, like way behind everyone else. That was her 2 sisters in school. They were both put at the very back of the class with their deck against the window, and were basically ignored. So it's some amazing experience. It was just a really neat fireside. All right. Okay, take 30 more seconds here, or maybe 20. Okay, we do have a few people that who care. I mean, you're wondering who cares. This is not one of the most exciting lessons of this semester. I apologize. And the place where most of these trigonometric integrals come up, they don't usually come up in practice with like a sine cubed times a cosine squared. What happens is we get something else that comes up in practice, and then to get something we can actually integrate, we actually convert it to trig functions. That's the next section in trigonometric substitutions. So, but then you end up with things that look crazy like in this section. So, okay, let's do this. So, is this an easy case or a hard case? Easy. Why is this easy? We have an odd power of sine or cosine. So that's what makes it easy. Relatively easy. So an odd power of sine or cosine. If we've got an odd power, then we can do a substitution. We can use our trigonometric identities and convert everything over to sine or cosine, and then do it from there. So we're going to do this problem, but just wanted a brief review of some trigonometric identities that come in handy. So you have the Pythagorean identity here. It comes from the unit circle. This length on the unit circle is cosine. This length is sine. This length is 1. You do the Pythagorean theorem. You get that. If you divide everything up here by cosine squared, then you actually get this one. So I always forgot, is it tangent squared plus 1 equals secant, or is it secant squared plus 1 equals tangent? Now I don't even have to remember that. I just have to divide by cosine squared. You get it. You can also divide by cosecant squared, and you get the relationship, the Pythagorean identity with cosecant and cotangent. They just don't. We don't use those as much. Okay, half-angle formulas. These are really nice to memorize. These turn out to be the easiest way, usually the easiest way to find the antiderivatives of sine squareds and cosine squareds. You're going to be doing that so much, you'll have those memorized. So, and then every once in a while, we'll end up using this identity, this double angle formula. Also, it's really nice to know secant of x, the antiderivative of secant of x, is the natural log of secant of x plus tangent of x. Okay. It's the one the book explains it's not easy to derive to figure out what that is. But if you take the derivative to the right side, you do get the left side. So, all right, should we do this one? Okay, so cosine is odd, so I'm going to think of cosine as cosine squared times cosine and convert one of those cosine squareds to 1 minus sine squared. That's the strategy. So, sine to the fourth, right? Sine to the fourth x, cosine squared x, cosine of x dx. Here I replace cosine of x with 1 minus sine squared x, cosine of x dx, sine to the fourth x. And now I can do a u substitution. The reason it's easy is because now if I make u equal sine of x, du equals a cosine of x dx, and that cosine of x dx, if we didn't have that cosine of x dx, or if cosine was even, we'd end up with cosine squared, or we'd end up with nothing to to do a substitution with. So this is why it makes it nice. So I've got a cosine dx that's equal to du. So I end up with u to the fourth times 1 minus u squared du. I can distribute that out. And I get u to the fourth minus u to the sixth. And that is u to the fifth over 5 minus u to the seventh over 7. But I have to convert that back to signs. So sine of to the fifth x over 5 minus sine 7th x over 7 plus c. So B was your answer. Right. So there you go. Okay. So let's talk quickly about how do you handle these cases, sine squared and cosine squared. A lot of the times, even if it's worse than sine squared or cosine squared, you end up having to take the antiderivative of sine squared or cosine squared somewhere in there. So I've already mentioned about how you might do this. Go ahead and talk to your neighbor. How would you figure out the derivative or antiderivative of sine squared or cosine squared? Okay, I heard half angle being muttered a lot. Okay, so one of the easiest ways, did I do that right? So half angle formula, so sine squared is 1 minus cosine of 2x over 2, all over 2. Cosine squared 1 plus, so the only difference between those is these signs, cosine of 2x over 2. So this first piece is easy, right? 1/2 x. Second part, I'm doing a u sub, so I can let u equal 2x. du equals 2 dx, so dx is equal to du over 2, and I still have to find the antiderivative of cosine of u over 2, but the du, and I get the du over 2. So the 1/2 here, the 1/2 here becomes 1/4. Antiderivative of cosine, sine of u, and I need to convert that back to x's, so 1/2 x minus sine of 2x, and this 2x comes back over 4 plus c. So this comes up so much, you should just memorize these. And cosine squared, you get the same thing except it's going to be they're added instead of subtracted. Okay. So, questions on these so far? All right. So we know the easy cases. The easy cases are when if you've got multiples of sines and cosines, if you have an odd sine or an odd cosine, an odd power of those, then we're good. But what about the hard ones? Yeah. This is 1/2 that's just times x. Yep. Yeah, this 1/2 I've already captured it right here in this one. Right there. So
You can pull out the whole 1/2 at the beginning if you want. You could rewrite it as 1/2 the integral of 1 minus cosine of 2x dx. You could do that. Thanks. Any other questions? All right. So I'm going to give you guys one to think about. Think about the strategy. You can start working on it if you want. But mainly it's the strategy here. Talk with your neighbor what you could do to figure that out. And also if you have a different way that you could figure it out. Talk about that. So the problem is sine to the 4th of x dx. Finding the antiderivative. So go ahead. Think about what strategy you would use. Okay. So I heard a lot of people talking about half-angle formulas. So that's one nice strategy, is you think of it as sine squared of x squared, and then you replace sine of squared with the half angle, so you get 1/2 minus cosine of 2x all over 2 squared dx. Okay? And then you've got to expand this out. So if you expand that, you're going to have a 1/4 minus, you're going to have this times that, you're going to have a cosine 2x over 2 plus, and you're going to have that squared, cosine squared 2x all over 4 dx. Did this help? How did this help? Garrett, go ahead. All right. We've lowered the degree. We started with a trig function to the 4th power. Now the highest power is squared. So we're still okay. We can use the half-angle formula for cosine over here and write that as 1/4 times 1/2 plus cosine of 4 to the x, because this is no longer just x here. This is 2 to the x, so this is really 2 times 2 to the x. So all over 2. And then we're we've got a substitute, u sub, but we are okay. All right. I probably went too fast for some of you. So snap if I went too fast. Okay. All right. So let's go back. Thanks for being honest. So here I rewrote sine to the fourth x, and I thought of it as sine squared x to the quantity squared. And then each of those sine squareds I'm replacing with the half angle formula. So I know each of those sine squareds I can replace with this. And that's a good strategy because here I've got sine squared. Here I just have a cosine. I go down, I cut my degrees in half every time I apply that. Okay? So our strategy is to get it down. Let's keep getting the degrees down until we get something we can handle. So either just so we can get just cosines or sines. Yeah? These are the main ones. So, yeah. All right. So now, once I replace that, I have this, but to find the antiderivative of this thing, I have to expand it out. So I actually have to multiply 1/2 minus cosine of 2x over 2 times 1/2 minus cosine of 2x over 2 and distribute everywhere. And then when I do that, I end up with that. Okay. And this 1/4, what's the antiderivative of 1/4? Yeah, it's just x over 4. This I can do with just a u sub, with u equals 2x. And this one, I could still do a u sub with u equals 2x. If I have cosine squared memorized, then that's great. But if not, I am applying this formula again, and the half angle formula for cosine, so which is right here. Except on the other one, I don't have x right there. I don't have cosine squared of x. I've got cosine squared of 2x. And so this is cosine squared of 2x, but the half angle formula says if I've got cosine of something squared, it's 1 plus cosine of 2 times that something. And so it's not 2 times x, it's 2 times 2x, which is 4x. Okay? And then I can still work on finding the antiderivative of all of that, which you're just one u substitution away. So yeah, I still have these terms over here to deal with, but those are the easier cases. And then I do half angle formula again for this case. Okay, is that better? Yes. So it's not just cosine of 4x over 2, it's this whole thing. Because I'm replacing, if I have the cosine squared of something, I can use my half angle formula right here. When I was in I'd never heard, well, I'm sure I had heard, but I sure didn't know the half angle formula when I was in your shoes. So I would not be surprised if some of you have not seen this formula before. If you want, I can show you where it comes from. I won't today, but I mean, I could put up a video of where it comes from if you're interested. But yeah, this is a formula that takes us from a cosine squared or a sine squared to something where we just have a cosine of a double angle. So, seems like this should be called the double angle formulas, and this should be called the half angle formula, but it's not. Did that help? Okay. All right. So that's one strategy. There's another strategy. For a lot of these, there's lots of strategies. Some might just be easier than others. Okay, strategy number 2, you could try to rewrite it as sine squared of x times 1 minus cosine squared of x dx. You don't want to replace both sine squareds with 1 minus cosine squared. If you do, you end up at the end of your expanding, you still end up with a cosine to the fourth of x, and you have to find the antiderivative of that, which is just as bad as finding the antiderivative of sine to the fourth of x. So you don't want to rewrite both of them as 1 cosine squared of x squared. You don't want to do that. Because you're going to end up with something else that's pretty bad. But you could do this. Distribute those through sine squared of x dx. That I can do. That I've actually got memorized. Oops. We've already done it once today. So x over 2 minus cosine of 2x over 4. Okay, that I can do. What about this other case? That's going to be a minus, not a plus. Minus sine squared of x cosine squared of x. And that looks pretty bad in and of itself. But there is another strategy you can use here, and that uses the double angle formula. Notice I have sine and cosine to the same power, so I can think about that as sine of x times cosine of x, quantity squared. But I have another formula I can use for sine of x and cosine of x. Yeah, the sine of 2x here. So sine of x times cosine of x equals sine of 2x if I divide by a 2. Okay, so I could replace any sine of x times cosine of x with this. And how does that help me? Well, sine of 2x over 2 quantity squared, that gets me just a sine squared and a u sub, and that's easy. Well, hopefully it's easy. I already did a sine squared right there, so we already did a sine squared earlier. So sine squareds and cosine squareds come up a lot, so you should memorize those. Yeah. It'll get you an equivalent answer. Yeah. So antiderivative. So a couple things could be happening. One, antiderivatives are only within a constant of each other. So especially when you're dealing with sine squareds and cosine squareds, you throw in a 1, or a 1 minus, and you can get the other one. So, but yeah, I'm going to show you another way to do this problem, and it'll get you something different. Something that looks even different. So. Okay. The third strategy to do this problem, it was introduced actually in our part in the section on parts. So the integration by parts integration by parts part, the section on integration by parts. Near the end of that section, they introduced what was called a reduction formula. Reduction formulas turn things like sine to the fourth x into something that's really, really easy. In fact, I can probably, instead of doing this strategy over here using the half angle formula, I could probably derive the reduction by parts, the reduction formula, and then apply it quicker than I could do this part over here. So, and that's what I'm going to do right now. I'm going to show you where the reduction formula comes in and how to use it. And it'll be a good review for integration by parts, too. I'm going to do this on another page. So if I have sine to the n of x dx, I'm going to find that antiderivative. I can think about this as sine of x times sine to the n minus 1 of x dx. Now, antiderivatives are harder than derivatives. Which of these is it easier to find the antiderivative of? If I'm going to do parts, I have to find the derivative of one and the antiderivative of the other. Which of these things is it easier to find the antiderivative of? Sine of x. Okay. Antiderivative is sine to that power of x. Well, that's just what we're trying to find, is sine to some power. So I'm going to let u be sine to the n minus 1 of x. Then du will be n minus 1 sine to the n minus 2 of x, and I have to do the chain rule here, times cosine of x. And then I'm going to let dv be sine of x, so dv is sine of x dx. V is a negative cosine of x. And now I can apply my parts formula. And the place where the reduction formulas come in, like most of them are derived using integration by parts. So you split them up somehow and use integration by parts. So I get uv. So here's my u, here's my v. So a negative cosine of x times sine of n minus 1 x minus the integral of v du. So v is my negative cosine. Du is n minus 1 sine the n minus 2 x times cosine of x dx. Let's simplify that a little. We've got a constant here. We've got a couple negative signs there, so let's pull that out. Should have done this one. So I'm going to get a positive n minus 1 what do I have over here? I have a cosine of x and another cosine of x. So that'll give me a cosine squared x times, I already pulled out my n minus 1, sine to the n minus 2 of x dx. And you're like, where are we going to go from there? Looks like we've got something pretty bad. We do. I am going to rewrite this as 1 minus sine squared. Now, if I was in your shoes, I wouldn't have been able to do this, right? But hopefully once you've seen one or two of these, then you'll start to see how they go. So I'm going to write this as 1 minus sine squared, and I'm going to end up having to find the integral of sine n of x on my right side as well as my left. And so then we're going to pull it over and solve for it. We're going to do that strategy. Might call it like running the cycle. So minus cosine of x, sine of n minus 1 of x, plus n minus 1 of, this will be 1 minus sine squared of x. So I'm going to distribute that out, and I'm going to get, I have to remember this n minus 1 is multiplied by all of these. So sine n minus 2 of x dx minus sine of n of x dx. Because I've got a sine squared and I have a sine to the n minus 2. We add those exponents and we just going to end up with sine of n of x. And I do have to remember though that this n minus 1 is multiplied by both of these. So over here I actually have, this is multiplied by n minus 1, this is multiplied by n minus 1. So I actually have a negative n minus 1 of these things, and over here I have one of those things. That's just a 1. So if I add n minus 1 of these things from here over to the other side, what do I get? I'm going to have n of those things. So it's a minus cosine of x sine to the n minus 1 of x plus n minus 1 of sine to the n minus 2 of x dx. Now, why is it called a reduction formula? Oh, one more step. I better divide by n. So, yeah. You mean this one right here? Yeah, so when I added n minus 1 sine of n's to this side over here, like to both sides. But I already have 1 over here. So I have the 1 over here, and then I have the n minus 1s, and I end up with just n of them. So. Right here, integral of sine to the n of x. Yeah, because I divided by n and those divide out. So the integral of sine the n of x is equal to this expression plus this fraction times sine to 2 degrees lower. That's why it's called reduction formulas, is I can rewrite the sine to some power as this expression plus another integral that is 2 degrees lower. And then I can just keep applying it again and again and again, and eventually I'll get down to sine squared or sine or even 0, sine to the 0. Which one? This one? Yeah, so I took this, I took it to this other side. Oh, this, yeah, that should be n. That's probably what you guys were talking about before. So I had the integral sine of n to the x on this side, and then I had a bunch of stuff, plus some other stuff, plus, minus actually, minus n minus 1 of sine to the n of x dx. So I had, this is the same thing that I have over here, but I need to add n minus 1 of them to both sides to cancel this out. So you end up with n of these things on the left-hand side. Okay. So it's a lot like if I've got an x plus equals 5 times a minus n minus 1x, and I'm bringing this over to isolate my x's, so I would end up with n minus 1 x's plus an x equals 5. I end up with n x's equals 5. That's all I did. Did that help? I don't think it helped very much. Oh, more the step before that. So I replaced cosine squared with 1 minus sine squared, and then I had to distribute this to each part. All right. Okay. Sorry. Okay, so I end up with this reduction formula. And once I have that reduction formula, then something like sine to the 4th becomes really, really, really easy. Because now I can just pretty much write it down. Let me erase this. So if I have sine to the 4th of x dx, then I just start applying my reduction formula. N in this case is 4, so I get a minus cosine of x sine to the 3rd of x over 4 plus 3/4 times, but now I need to lower the 4 by 2, so I'm down to sine squared. If you know what sine squared is, you can just write it down there. But I can also use the reduction formula for sine squared. It's still sine to some power. So now I just start applying this same formula, but with n equals 2. Excuse me. So a minus cosine times sine, oops, better write x in there. Sine of x over 2 plus 1/2 times, well now sine has gone from sine squared. If I subtract 2 from that power, I'm down to sine 0, which is just 1. What's the antiderivative of 1? X. So there we go. I just wrote down the antiderivative of sine to the 4th of x by just applying the reduction formula twice. So it's really slick. This is one of the nice ways to handle the hard cases. So the hard cases for sine and cosine is if they're both even powers. So one strategy is to convert all your powers of sine or cosine to one of those. If I have a sine to the 4th x times cosine to the 4th x dx, I could replace one of these with 1 minus sine squared dx squared. Sure, I've got some stuff to multiply out there, but I'm just going to have powers of sine. I'm going to have a sine to the 8th, I'm going to have a sine to the 6th, I'm going to have a sine to the 4th, and I can just use the reduction formula on each of those, and you can just write them down. Yes? That, or be able to derive it. So, no, you don't have to do the reduction formula. You don't. I was just trying to argue, like, it actually is really nice to have the reduction formula. And they're all in the back of your book. So, or in the back of your ebook. Yes? Yep. There's a similar reduction formula for cosine, derived the same way. So, yep. That is. Okay. Let's talk about tangent and secant. What are the easy cases and the hard cases here? So, you should have read about it, but tell your neighbor while I write this down. Oh, so the question is, what if you're mixing, like, if it's not tangent secant, what if it's tangent sine or something? Yeah, they will. In those cases, you could always have a strategy of converting everything into sine and cosine, right? Tangent, secant, cosecant, cotangent. You can all write them in terms of sines and cosines, and then you can work with sines and cosines. So, possible. It is M and N. Okay, someone tell me an easy case here. It's easy if the power of secant is what? Even or odd? Yeah, but 0 is what? 0 is even. So it's easy if n is even. Okay? You can use that as a thinking strategy. What if the power was odd? Or 0? Is that good for me or not? And it's easy if m is odd. Now why? Well, it all has to do with the derivatives of tangent and secant. If I have an even secant, like if I have a secant to the 4th of n, this is okay. I like this because as long as this is even, I can convert all of them to tangents except for a secant squared. I can convert all of them to tangents except for a secant squared, and then I can just do a u sub. So secant squared is tangent squared x plus 1. Secant squared x dx. So now I'm happy because the derivative of tangent is a secant squared. I have a secant squared x dx. I can just do u equals tangent of x and turn it into a polynomial because du is secant squared x. So I'm happy if that's the case. And also, so if m is odd, so if the power of tangent is odd, then I'm happy because I convert all of my tangents over but one. So if I've got a tangent cubed, the derivative of secant is secant times a tangent. If I've got secants and tangents in there, I want to have just one tangent left. And then I can borrow one of the secants and that single tangent, and then I can do a u sub. So tangent is secant squared x plus 1, no, minus 1. And secant to the 5th x dx. So now I'm happy because now I can do a u sub with secant. Because I'm going to have a secant of x tangent x. So I have a tangent x. I can just take one of those secants. Secant of x times secant to the 4th x. And now I have a secant of x tangent x dx, and I'm good to go. The hard case is when secant is odd, tangent is even. Okay? We don't have time to do one of those. So, sorry, you guys will work on those tomorrow in the lab. But have a great day.